we just didn't start it. Okay, good. This is taking some time for people to show up. Is there any conflict? Well, we are already 3 minutes over, and let's people will keep joining us. Let's start, because out of respect to everyone that is already here. So I will do a short introduction, and then I will pass you the floor. Okay. All right. So do you mind if we record this? Okay.
No, go ahead. That's fine.
Let me just start recording. Okay, so hello everyone, and welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube. You can find the link on our website or access it on our YouTube channel, Linea MCTI. Today we have the honor of having Dr. Danielle Leonard from the Newcastle University. Dr. Leonard is a lecturer in astronomy at Newcastle University, and her research focuses on testing the standard cosmological model, primarily with measurements of gravitational lensing and galaxy clustering. Her research also focuses in astrophysical modeling, uncertainties affecting these measurements, such as intrinsic alignment of galaxies. She's a member of the Rubin Observatory, LSST, Dark Energy Science Corporation, and co-convener for Modeling and Combined Probes Working Group, and is heavily involved in the creation of the Core Cosmology Library, which is a Python package used by Dark Energy Science Collaboration. Dr. Leonard, thank you very much for being so kind and having accepted to give us a webinar talk today on such an exciting topic. The floor is yours.
Okay, great. Thanks. And thank you for inviting me. So I'm going to be speaking today about one of the things that Rodrigo mentioned that I work on, which is intrinsic alignments. So I'm going to focus on that aspect of my work today, and specifically how and why we need to understand more about intrinsic galaxy alignments for getting cosmological information out of weak lensing. So as I'm speaking, I can't see the hands in the Zoom, but if there's a hand up and somebody else can see, or if you have a question and you do want to just shout out if I'm not seeing the hand, please say. I will try and stop and ask for questions periodically as well. Okay, so I'm not quite sure like the background of the audience, so I'm going to give a bit of a refresher on weak lensing and then an introduction to intrinsic alignments. And then I'll talk about why we care about this for cosmological analyses. And then in the second part of the talk, so that's kind of an introduction, and then in the second part, I'll talk about sort of a selection of ways that we can address this issue and a selection of projects that are ongoing that either myself or students that I work with are working on to try and tackle this problem from different ways. So as a bit of a refresher, in case somebody is from a totally different field of astrophysics, gravitational lensing is the effect where you have light, which is propagating from a distant light source. In this talk, I'll be speaking mostly about the case where this is a galaxy, And that light is propagating from that galaxy through the universe. It's passing by large scale structure, galaxy clusters. It's passing by all kinds of stuff, and it's coming to us on the way to the observer on or near the Earth. And gravitational lensing is the phenomenon where as that light passes by massive objects or over densities, its trajectory is altered. And so on the left here, we have an illustration of that setup where in the simplified case, you just have a single lensing mass. And you can see that the perceived position of the image has changed. And so on the right, we have an illustration of what this could look like in the case of really dramatic effects from gravitational lensing. So we have this bright object in the middle of the image, and that in this case is where our sort of lensing mass is. So we have like a cluster, and we can see that in the background, we have other galaxies, which are, their images are stretched, elongated along the tangential direction to that central object. So we have like in an arc around the central object, the lens, we have all these images of the background galaxies being stretched. And so these kinds of like arc effects, as well as potentially even like multiple images of the same object showing up, are the kinds of things we see when we are looking at strong lensing, strong gravitational lensing. Weak gravitational lensing is the same physical effect, but it's the end of the spectrum where we don't see these dramatic effects. So it's not that we can look at an object or a system and say there's gravitational lensing happening there. It's more that there's always going to be some gravitational lensing when we're looking at galaxies that are from where their light is coming from far away. They're always going to be passing by and through sort of the cosmic structure on the way to us. And so there will be some gravitational lensing, but it's at a much lower level. And the general effect of gravitational lensing in the weak regime is that the images of these galaxies that we see are both the ellipticity and the orientation of the sort of, if you model the galaxy as an ellipse, the orientation and the ellipticity of that ellipse is altered. So that's what we call shear. And also the brightness and size of that image is changed, which is the magnification. And these two effects are related to each other. So typically we just measure this in terms of the shear, because that's sort of a more straightforward measurement to make. And because we are not able to look and see like a single system where we have gravitational lensing happening, we are instead looking at measuring this kind of effect statistically. So we're looking at measuring weak lensing using large samples of galaxies. So what does that look like, making that kind of a statistical measurement? So there's a lot of different ways to do this. I'm going to be focusing on the sort of most standard type of tool, which is 2-point correlation functions, but there are other kinds of ways to measure this effect. 2-point correlation functions, if you're not familiar, the basic idea is probably most easily seen if we think about if we put aside lensing for a second and think just about measuring galaxy clustering, so measuring the clustering of the positions of galaxies. If we think about that case, if we imagine I have a galaxy here, the 2-point correlation function answers the question, I have a galaxy here, what is the excess probability above a random field that I have another galaxy at a separation r if I'm in 3D space, or theta if I'm looking at angles of the sky. And so this is interesting because, even if your galaxies were modeled by a random field, you would still have some probability of having another galaxy at a separation r or theta. But because of course, structure formation and gravitational instability and collapse over time, this correlation in the positions of galaxies tells us something about that physics. And so that is the 2-point correlation function for galaxy clustering. But we can also do a similar type of measurement for lensing. So in that case, instead of saying what's the excess probability of having a galaxy at a certain position and only caring about whether the galaxy is there or not, in the case of lensing, we're talking more about, okay, I have a galaxy at a certain position and it has a certain shape and a certain orientation. And so at a separation, in this case, you're going to be looking at angular separations. So at a separation theta, what is the excess probability of having another galaxy which has a certain other shape and orientation? And so you can see there's like a little bit more information in that kind of a question than just in the positions, because you're talking about orientation and shape. And so actually we have two different 2-point functions that kind of capture both that information, but we call that idea of like 2-point functions made up of 2 measurements about shear or shape, cosmic. So that's measuring what we call cosmic shear. So, and we call the 2-point functions associated with that psi plus and psi minus. And then, like I already explained, you can also consider positions and positions. That's not lensing per se, but it's quite interesting to combine that information with a weak lensing 2-point function in an analysis. And then, of course, you can also think about doing the cross correlation between those 2 things, right? So if I imagine I have a population of source galaxies, so these are my faraway galaxies where I've got shapes measured, and where I'm looking at their lensing, I might do a measurement of the cosmic shear using that source population. I could also have a lens population. We'll call it a lens population. Which is galaxies that are typically lower in redshift, where I don't necessarily have shape measurements. And that I could do a measurement of galaxy clustering, but I could also consider the case where I ask the question of, if I've got a galaxy here in my lens population, what is the excess probability of having a galaxy in the source population at a certain angular separation having a given shape and orientation? And the reason that you would expect that to be non-zero is because if you have a galaxy sort of on the path of the light that's coming from your source galaxy, and that light is passing by, you're going to see the background galaxy being lensed by the mass associated with the foreground galaxy. And so that is what we call galaxy-galaxy lensing. So we've got these 3 types of 2-point functions. We've got cosmic shear, which is shape, or shear. We've got galaxy-galaxy lensing, which is shear or shape and position of the foreground galaxy. And then we've got galaxy clustering, which is just position. So this is 3 2-point functions. And so for that reason, we call this combination of observables 3 cross 2-point. And that's sort of a common combination of observables to consider for a weak lensing type survey. And just in case you're not familiar with these in terms of how they would actually look, if you calculate them, this is an example. So this is obviously for a certain redshift bin, and this is just from linear theory. But you can see that for all of them, you have a higher value at the smaller separations, which makes sense because things are going to be more correlated with each other as you're looking at positions close to each other on the sky. Does anyone have any questions at that point? I'm not sure if this is all old hat for everyone, or if there's some people who might not have come across this before.
I think we're okay.
Okay, cool. Thanks. Right, and so to talk a bit about the context of this, so the context in which we're making these kinds of measurements is what I'm trying to illustrate here on this slide. So we kind of have a set of surveys for weak lensing that are currently ongoing. So we have these surveys, KIDS, DES, HSC, that are either kind of currently taking data or currently analyzing data. And they're all kind of hovering in the middle of this plot here. And so what am I trying to show in this plot? So to obviously, if you're taking a statistical sample, if we assume our statistics are governed by largely like a Poisson type noise, which to a large extent they are for this kind of measurement, to kind of beat down that kind of statistical uncertainty, we are talking about having more galaxies. So more galaxies is what helps you beat down that uncertainty. And how do you get more galaxies? You either go to larger areas or you go to fainter fluxes. So you go to more galaxies per square arc minute, which is going to give you, which is going to correspond to going to fainter imaging. And so we can see where like the current generation of surveys is sort of hovering. And in green on the top right, we see two of the upcoming generation of surveys, Euclid and LSST. And so we can kind of see that, so Euclid being a space-based mission, which is focusing on weak lensing and cosmology observables. LSST, as many of you already know, being a ground-based telescope, which has a lot of different applications, but also amongst them being cosmological analysis. And so we can see that for both of these cases, we're looking at kind of a qualitative shift. We're going way deeper and to much larger areas. And so the statistical uncertainty is going to be much reduced compared to what we're kind of used to working with. And because of that, we need to be even more careful than we have been in the past, and that we are currently having to be, about things like modeling uncertainties. So this is all to lead up to like why you might care about intrinsic alignment. So even now, even for current surveys, we do find that it's pretty important to get the correct intrinsic alignment model. But that will be, even more important in the era of LSST and Euclid, because your statistical errors from just Poisson noise are going to be subdominant. Right, so that's sort of the end of the general introduction. And then what I'll talk about now is an introduction specifically to intrinsic alignment. So I'm just going to check the time. Okay, cool. So intrinsic alignment as a concept in general is the case where, so we talked about the idea that you measure weak lensing by correlations in the shapes or shear of galaxies. And we talked about 2-point correlation functions specifically. And if you were to do that naively and assume that all of the correlation that you see is due to lensing, you would be missing, you would be missing a number of different sources of potential correlation, one of which is intrinsic alignment. So intrinsic alignment is simply the fact that it's not true that all of the correlations you would see are due to lensing, because there are intrinsic reasons that galaxies can be aligned with each other. And this contaminates both the shape-shape correlation, so the cosmic shear, and the shape-position correlation, so the galaxy-galaxy lensing. So the way that this contaminates cosmic shear is illustrated here. So there's two different ways that intrinsic alignment can contaminate cosmic shear. So if we look at the sort of the top, I don't know if you guys can see my arrow, hopefully you can. If we look at the top two panels here, this is the case where if you're looking at correlations in the same redshift bin between galaxies, and you happen to have a massive structure that is nearby two of your galaxies, you could have the galaxies becoming orientated towards that massive structure due to tidal alignment. So a lot of this intrinsic alignment on larger scales, so 2 halo type scales, comes down to tidal physics. And so having a gravitational field from the, in this case, this like blob of dark matter, and that gravitational field being not constant across the halos containing our 2 little blue galaxies labeled I here, is going to cause the stretching of the halos of those 2 galaxies, and then the galaxies inside tend to preferentially align with their halos. So that's sort of the tidal alignment effect, which we expect to see with like specifically elliptical galaxies, and we do see. And so here you can see how like we have a correlation here in between these 2 blue galaxies, the II correlation, which is not due to lensing, and which is also in a different sense than what you would expect from lensing. So at the beginning, when we saw that strong lensing example, you had these tangential arcs, and so here we, instead of tangential arcing, which would be at a much smaller effect, but that would be the general like idea. You would have instead the galaxies like radially aligning with a central object. So that's one way that intrinsic alignment affects cosmic shear. Another way is the bottom 3 panels here. So in this case, we've got 2 galaxies that are at 2 different redshifts. So if we're correlating samples of galaxies at different redshifts, we may have one galaxy that is at the same redshift as a massive object. Here again, we have a blob of dark matter, and then we're going to have that galaxy being tidally, like radially aligned with the massive object. But then in the further away redshift, that massive object is also going to lens the background galaxies. So then we're going to have actually a dilution of the shape-shape correlation signal, because we've got one galaxy that is radially pointing at the dark matter. We've got one that is tangentially orientated with respect to the dark matter due to lensing. So that's your cosmic shear effect. So you've got 2 terms, a GI term and an II term. You can also have intrinsic alignment contamination in galaxy-galaxy lensing. And in this case, it's down to how good your redshifts are. So usually for source samples and weak lensing measurements, almost always you would not have spectroscopic redshifts, because it's just too expensive to get spectra for every single galaxy in a weak lensing sample. And so we're almost always going to be relying on photometric redshifts. And so photometric redshifts are not perfect, as we all most likely know. And so what can happen is illustrated here. So if you're doing a galaxy-galaxy lensing measurement, so you're looking at a lens galaxy population, you might try to look at source galaxies that are in the background of that lens galaxy, so at a higher redshift. So you make a cut such that you're not looking at galaxies that are close by and therefore wouldn't be aligned intrinsically, but you're never going to get that perfect. So you'll have some source galaxies that, although maybe the photometric redshift says that it's, you know, at a higher redshift, actually they're in the same redshift range as your lenses. And so you'll have a contamination there, and you could have radial alignment towards your lenses. Right, so those are kind of the 2 effects. Any questions on that? Just to see if I can, see if I can see the participants. I don't see any hands, but so I'm going to assume that's okay. So just quickly, as this will be helpful for some of the stuff I'm going to talk about later, I thought I would just give a quick review of what the modeling kind of looks like, what the state of the art kind of looks like in the modeling for intrinsic alignments. So kind of from the top of this page going down, we have sort of earlier models going to more cutting edge models. So the linear alignment model is a model that only takes into account the kind of tidal alignment stretching that I was mentioning. And so this is sort of first order in the tidal field effects. And it assumes that the alignments are set by the structure at an early time, so at a time when sort of most of the galaxies were forming, or rather like most of the structure was forming. This is all very hand wavy, but the point being, you only use the linear power spectrum in the linear alignment model. We also have the nonlinear alignment model, which is confusingly named because it's actually still linear in the tidal field, but we shove in the nonlinear growth of structure as like a sourcing mechanism for that tidal field. And that doesn't have any sort of like rigorous theoretical basis, but it seems to fit our data better. And that's something that, so this version, this like sort of ad hoc version of the nonlinear alignment model, NLA, is something that we still use quite regularly. You can go one step further than that and look at the tidal alignment and tidal torquing models. That's TATT. So if you think about tidal alignment being just the first order term in a perturbation theory expansion of like the tidal effect, tidal torquing would be including the next term. So that means that instead of just having the stretching effect, you also have torquing on the angular momentum vector. And so we don't see tidal alignment, we don't measure tidal alignment at like a non-zero value for spiral galaxies yet. And the thought is that tidal torquing would be a more important effect for spiral galaxies. And this is what we see in simulations. So we haven't measured that conclusively yet, though. And so TATT is a model that you do see coming up, and people are considering in analyses now. All of these so far, though, are really only kind of two halo type models. Like even the perturbation theory models where we are going to the next order, it's still like relatively large scales. You can also consider going to one halo scales. So there's the Fortuna et al. Model, which is kind of tries to unify a large scale model like NLA or TATT with a phenomenological one halo term that would be from like a halo modeling type approach. We'll talk a bit more about that later. And then, yeah, there's also work on like improving the perturbation theory type models for intrinsic alignments. So these bottom two are kind of like currently in development. So that's sort of our model spectrum at the moment. And then to get into like the final thing before I go into some sort of strategies and like research topics is like, do I actually need to care? This is like a pretty small effect. Does it actually affect cosmology? And the answer is potentially yes. So I'm sure many of you may have seen this plot before, but this is a plot from the pre-unblinding checks of the DES year 3 cosmic shear data. So this is the case where this is an MCMC analysis where the input data is simulated. So they simulated input data which had TATT model parameters that were consistent with the year 1 DES analysis, and also that just had NLA, intrinsic alignment in the simulated data. And then they analyzed that with both NLA and TATT. And so what you see most obviously is that with the X being like the true cosmological parameters here, is this purple ellipse. And this is the case where your data is the more complicated model, the TATT model, which would still have been consistent with the known parameter space at that time, but analyzed with the NLA model. And so clearly you can see like this can have a big effect. There is a caveat, which is that like the year 3 analysis actually ended up, even though TATT was used for this reason, it ended up that some of the parameters actually were consistent with 0. So they could have, some of the TATT parameters could have at the end been left out and like had a smaller parameter space, but just a small caveat. But you can see that like you could have quite a big bias being induced in your cosmology by your intrinsic alignment modeling. And so then we get into the kind of more interesting stuff, right? Which is like, what do you do about it? And so this is sort of a chart of all the, well, not all, but some of the different things you can try to do about it to try to get unbiased cosmology results. And so what I'm going to do, I won't talk about everything on this chart today, but I'll just talk about a few of these boxes. So the idea here is that what you want is, so we talked about theoretical models. So you have different theoretical models. You might make direct measurements as to the extent that you can of intrinsic alignments to try to figure out which of these models is plausible and to put priors on the parameters of those models to feed into your cosmological analysis. You want to see if any of those models have like interplay with other effects that you're modeling, like photometric redshifts and intrinsic alignments, for example, can induce like large degeneracies with each other depending on the model. And then we're trying to construct an analysis pipeline to take all this into account, and then testing that analysis pipeline on synthetic data that adequately models intrinsic alignments realistically. So this is, and of course, with the intention of then having a robust cosmological analysis. So this is sort of a very sketchy roadmap, and I'll talk about a couple of these boxes today in the sort of remaining time. So so that was a very long introduction, but that was intentional. And then we'll take a little bit of time to, like I said, touch on a few different ways you can try and deal with this. So the first thing I'll talk about is this box here, which is direct measurements, and the difference being between the box above it and the box I've highlighted is whether or not you have spectroscopic redshifts for the source galaxies that you're looking at. So one thing that the box up here, like the top box, would be the case where you have a sample where you have spectroscopic redshifts and you have shapes. And then you can actually go in and say like, okay, I know these galaxies are close to each other, and then measure an intrinsic alignment signal when you know the galaxies should be close enough to each other to be intrinsically aligned. So that's great. But the problem with that is that those galaxy samples tend to be not representative of source samples, because, you know, if you have a sample which has spectroscopic redshifts, they're probably like LRGs or something. They're probably like bright galaxies in massive halos. And so it may not, it probably isn't going to look very much like what a source sample would actually look like. And so the advantage of doing these like sort of not as direct, but still not like within, still not just like modeled within a giant analysis type measurements, is that you can get like a direct measurement, but using a source sample, which is closer to what a weak lensing source sample would actually look like. And so the strategy here, at least with the methods that I'll talk about now, is to construct estimators which try to cancel out the lensing effect. So the idea is that you would measure, and focusing on galaxy-galaxy lensing here, you would measure the shape cross-position two-point function in each case in two scenarios, which have different intrinsic alignment signals, but same lensing signal, or lensing signals that are related to each other in a way that we understand, so that we can construct estimators that only depend on the intrinsic alignments. And of course, if you can then get an estimator for the intrinsic alignment signal, you can use that to understand like which intrinsic alignment models are plausible, particularly at small scales where we don't understand that as well yet, and to set priors on model parameters for cosmological analyses where you have to include this modeling. And so one way you could think about canceling out the lensing is by using different redshift bins. So this is a method from Blathic et al. 2012. And the idea here in general is that you would have a measurement of galaxy-galaxy lensing from a redshift bin that's close to your lens sample, and one that's like further removed from your lens sample. And of course, those two measurements are not going to have the exact same lensing, but we can relate them to each other in a way that by using like the critical density for the given measurement, we can construct an estimator that does like cancel out that lensing signal. And so you can get the intrinsic alignment signal that way, because of course the closer sample is going to have higher intrinsic alignment than the further removed sample from the lenses. And so this 2012 paper was just introducing the method and put some upper bounds on some parameters using it. This is more recent work. It's currently in prep. It's led by a PhD student, Sarah Safari, or sorry, no, a master student, Sarah Safari at Zurich. And she's done a measurement using this method, using the DES year 1 data. And at the moment, we're seeing some weird stuff. So we're seeing in this convention, intrinsic alignment measurements would be negative in the convention that we expect. So if you do have that, like, you know, tidal stretching, like things pointing at other things effect, that would be negative. We do see that at small separations, but then at larger separations, we're seeing these positive data points. And we've done a lot of tests. We're still doing a lot of tests. It looks like perhaps there's some unmodeled photometric redshift errors that are consistent with the larger scale positive data points, and maybe we're actually seeing intrinsic alignment just at the smallest point, but this is still very much preliminary. But it's cool to see that this method, although previously it was just doing upper limits, could potentially at least have some level of measurement. Another way you can think about canceling the lensing to get at the intrinsic alignment in this case is by using the fact that different shear estimators are sensitive to different parts of a galaxy's light profile. So if you use a shear estimator that is more sensitive to the outer parts of a galaxy's light profile, you are going to end up with a different correlation signal from the alignment, as if you use a shear estimator that is more sensitive to the inner part of the galaxy's light profile. And that is because if you think about the fact that, like, the way the tidal physics works, like, you're stretching those external parts of the galaxy more, whereas the lensing works the same, because it's the light. It has nothing to do with whether you're at the outside or the inside of the galaxy light profile. And so this has been shown in simulations as well as in observations to be the case. You get a different intrinsic alignment amplitude in these different shear estimation methods. And in observations, it's also been shown that basically when you have these differences in the shear estimation method, what you're actually doing is multiplying the measured intrinsic alignment by a constant. And so you can take this and you can construct an estimator where you have the same galaxies treated with two different shear estimation methods. And you won't get a measurement of the amplitude of the intrinsic alignments if you subtract these, but you will cancel out the lensing, and you can use it for understanding the scale dependence of the intrinsic alignments, which would be really useful for model testing and constraining parameters. And so what this plot is showing here is a forecast which shows that in certain regimes, this can be more powerful than the method that I mentioned previously with the redshifts. A here is the constant by which the intrinsic alignment signal is multiplied, and rho is the correlation of the shape noise of the two methods. So there's like some interesting play between how you pick the two methods, and like obviously there's a load of stuff about, like, you know, kind of tying in with current methods for like what the best shear estimation methods are going forward. So yeah, this is I'm excited about this idea at the moment. This is just the statistical forecast, but it has it's much less subject to these kind of photometric redshift errors we saw in the previous method in principle, because it isn't relying on correcting the lensing using like a sigma crit, for example. It's should have just a direct cancellation. So that's pretty cool. And this is also something that a PhD student of mine is working on doing a measurement of with DES year 1, because we do have the 2 methods. This is super preliminary at the moment. And I'm also aware of time, so I'll just flash this up as like a stay tuned thing. Right, so that was the direct measurements. Another thing that you want to be thinking about is having mock galaxy catalogs to test your pipeline and make sure that you're not being biased because of intrinsic alignments. So once you have like an analysis pipeline you're happy with, which has modeling of intrinsic alignments in a certain way, how do you test it? And so actually in Desk at the moment, so in the Dark Energy Science collaboration for LSST, our sort of flagship simulations don't have realistic alignments for the halos below a certain resolution. And so this is something that we're working with to try and the mock galaxy catalogs don't have realistic alignments at all, I think. And so we're kind of working with this to try and see if we can infuse that so that we can actually test our pipelines appropriately. And so one way that you can try to do this is building models that are similar to like the traditional sort of halo occupation distribution models, so HOD models. So in a traditional model, that would be just to place galaxies in halos with appropriate properties. So according to like the mass of the halo, usually just that, but then you can also look at like environmental factors if you're being fancy. And that is like a way of populating a n-body simulation with galaxies instead of having a hydrodynamical simulation. But traditionally, that doesn't have any information about the alignment of the galaxies with each other. And so Nick Van Alphen, who's a PhD student at Northeastern involved in Desk, has been working on implementing a HOD type model to place galaxies in dark matter simulations with appropriate alignments. And so it's basically modeling the misalignment angle, which is labeled in this graphic theta MA. And like I said, there's kind of a subtlety, which is like whether or not you have subhalo information at the appropriate resolution for your galaxies, you have a different, you have to sort of be aware that sometimes you're not going to have that. So how you actually define this misalignment angle varies. You may define it with respect to the subhalo or with respect to like a radial vector from the center of the parent halo. And do you still recover correct alignment information if you don't have that subhalo information? And how do you do that is the kind of stuff that's being worked on in this project. So one thing that Nick is finding at this point is that if you look at the portion of the correlation function that is central galaxies positions correlated with satellite shapes, he's finding that he's able to fit the one halo regime pretty well, but the two halo regime is not being modeled adequately by this type of HOD. And so what he's taking away from that, and what we're taking away from that, is that the satellite galaxy alignments actually also depend on the position of external halos. This may not actually matter because obviously most of the two halo term is central, but it's kind of an interesting thing to be seeing. For time, I think we said like 45 plus 15. I don't know how
Yes.
much time do you want me to keep going for?
Yeah, well, we usually would like to have some 5 or 10 minutes for questions at the end.
Okay, yeah. So if I do like 5 more minutes, is that good?
Yeah,
or
it's okay, 5-10 minutes, it's okay.
Okay, cool, sounds good. Okay, right. So yeah, so this is one way you can try to infuse intrinsic alignments in mock catalogs. I won't go into this in detail, but another way you can try to do this is using different kinds of machine learning. So there's some efforts within Desk, again, trying to use a type of neural network called graph neural networks, which to capture the intrinsic alignment information from hydrodynamical simulations, and use that, like capture that in neural network and use that to create mock galaxy catalogs that have realistic alignment. So there's been a proof of concept of this in a paper that came out recently, and then it's being worked on to like optimize. But yeah, I'm not going to go into that in detail. Just to basically say you can also do this in other ways, including with machine learning. Right. And so yeah, so that's like, yeah, that's another one of these boxes. So looking at the ways that you want to get appropriate mock galaxy information into n-body simulations with appropriate alignments. And then the final kind of box here that I'll mention is building appropriate analysis pipelines. So usually, as many of you will know, ultimately what we're talking about here is having a, like in this case, a 3x2 point analysis where we are modeling jointly the intrinsic alignment and the weak lensing signal from cosmology, as well as like all the other, you know, the galaxy clustering, galaxy lensing, and constraining cosmology while also having priors on the intrinsic alignment parameters, and then also getting constraints on the intrinsic alignment parameters. So there are questions you can think about like what is the best way to do this type of modeling to get the most information and break the most degeneracies between our systematic parameters. So yeah, I basically just said this. So one thing that you might want to do is consider links between your systematic parameters at a physical level to try and break degeneracies. So this is a project that my PhD student Nico Sarcevic is working on. And the background of this is, so the idea here is that potentially you can jointly model intrinsic alignments and the redshift distribution using luminosity function based parameterizations. So this is based on an idea from a paper from Van Dalen and White in 2017, which was basically pointing out that when you have a magnitude limited survey, your redshift distribution is really a convolution of the volume of that survey with a luminosity function. So you can try to parameterize your redshift distribution by the parameters of a luminosity function. And in that case, they were looking at, well, your galaxy bias is also luminosity dependent. So can you try to get some information out that way? And so we are kind of trying to extend this to looking at, okay, your intrinsic alignment also luminosity dependent in a lot of models. So could we have some joint modeling of these three systematic effects that takes into account the same parameterization, and therefore could we have some gain in constraining power by sharing the information between these three modeling ingredients? And yeah, this is an example here. So yeah, so basically the idea of this is to extend this framework to intrinsic alignments. And yeah, if you take a simple example, like this is not necessarily the model you would use, but like I just said, the luminosity is coming in, or the luminosity function is coming into all of these ingredients. And so this is currently work in progress. Unfortunately, I don't have any exciting plots to show, but Nico's working on some forecasts for this method for an LSST-like analysis, and we'll see how promising it looks. Hopefully, it might be helpful. Okay, so after that kind of whirlwind tour of some different bits of how you can approach intrinsic alignments and mitigating them, I think it's about time that I wrap up. So this is just a summary of what I've said. So at the beginning, we talked about how you need to worry about modeling these types of systematics much more precisely than you maybe did in the past or even currently, although you already kind of need to model them fairly well. And so you probably need to care about intrinsic alignment modeling for LSST and Euclid. And we talked about 3 different ways you might tackle this problem. So we talked about direct measurements to try and get understanding of the modeling and also priors. We talked about having appropriate mock galaxy catalogs to test pipelines, and we talked about possibilities of jointly modeling intrinsic alignments with other effects. And then I didn't really get to talk about everything that's going on. So that was only 3 of those like boxes. So there's lots of other stuff going on in all the other boxes. And even this is all like, this is not everything, but there's just some other projects within Desk that I thought might be of interest to people. So at the beginning, I mentioned the theory, sort of different modeling that exists. And so working on implementing some of those in the core cosmology library, which Rodrigo mentioned at the beginning. There's also this idea of self-calibration. So I mentioned like the II and the GI term in the cosmic shear. So the idea being that like you can actually link the GI term to galaxy-galaxy lensing measurements, so you kind of get some extra information that way. There are folks working on adding tidal field information to simulations. So not adding at the mock galaxy level, but adding the tidal field at the n-body, projected n-body simulation slices level. And then, yeah, just trying to understand what biases would be induced by different modeling errors, similar to what you saw in that DES year 3 plot, but kind of doing like a sort of a wide survey of like, okay, like how bad would this be? And yeah, so there's like lots of other work I probably haven't even mentioned, but I think I'll stop there. And yeah, if anybody has any questions, I'm happy to discuss that now.
Okay, well, thank you very much, Danielle, for the very interesting talk. We have now time for some questions from the audience. If you joined us on YouTube, you can put your question in the comment section. And if you join us here on Zoom, please raise your hand and ask your question. So questions? Well, while we wait, you were talking about some models of intrinsic alignment.
Yeah.
This is far away from my field of astronomy. So first of all, when we talk about all these alignments, we are trying to understand the dark matter behind it, or is it more global than that?
I see.
And
so do you mean like, are we talking about the dark matter, or are we talking about the galaxies? Is that kind of the question?
Yeah. What is the big point behind it? Is to model the dark matter?
I see. Yeah, so I think for me, the big point is that if you don't model the intrinsic alignment of the galaxies correctly within what you're measuring in terms of like a shear or a shape or, you know, galaxy lensing correlation, if you don't adequately model the intrinsic alignment contribution to that correlation signal when you're trying to measure lensing, you will get catastrophic biases in your cosmological parameters. So for me, the point is mostly ensuring that you don't get catastrophic biases in your cosmological parameters, but also like there is interesting galaxy information to potentially be had. It's a little bit removed from like, I think what people who like directly study like galaxy evolution and, you know, from people who directly study like galaxies for the sake of galaxies they wouldn't approach it in the same way, right? Because like we're always looking at like projected stuff with lensing, and so it's like there might be other ways to do this that makes more sense if you were actually trying to answer my question. But there could still be interesting like byproducts. So for example, like the thing I mentioned about what Nick is seeing with looking at this like trying to fit a model which is basing the alignment of like the satellite galaxies only with the information within the one halo, he's finding that like that doesn't capture the information on the two halo scale. So that's kind of like potentially an interesting like dark matter galaxy connection thing where it's like, okay, that information is that like your satellite alignments are potentially affected in a non-negligible way by central galaxies in other halos. So that's like, that could, you can get like sort of side information about like galaxy halo connection type stuff.
That's much clearer now.
Okay, good.
Yes, a clearer picture. And also, you talked about some models, and there is the THT. With tidal torquing. What does physically mean? It's torquing from torque?
So it's so it's an effect of there being a gradient in the gravitational field, which results in it's a torque in the sense that it changes the direction of the angular momentum vector. That's about as much as I can say without worrying I'm going to say the wrong thing. I'm definitely more on the observational side, but I try to understand the models.
Thank you.
No worries.
Okay, so someone has another question.
Okay.
If not, I have another question. I promise it's my last question. What will be the degeneracies that we were talking about when we measure this?
Right. So I guess I was mentioning like so one easy way to see this. So I was mentioning like, you could maybe break degeneracies with modeling photo Z and intrinsic alignment, modeling the part that that is linked like using a common parameterization. So, but like one kind of relatively easy way to see how there could be a degeneracy is in the current modeling for photo Z. Like, so for when I say that, like, what I mean is like, we have our redshift distributions and we, our very hardworking photo Z working group have done their absolute best to get, model the redshift distribution. But of course, we still have included in when we do our cosmological parameter inference, we still have parameters in there to account for any potential remaining residual uncertainties, right, on the redshift distribution. And one thing that we see is like, you basically have to allow for at this stage, the kind of typical modeling is to allow for a small shift in the mean of those redshift distributions. And so that modeling of the photo Z uncertainty, you can imagine if you shift the mean of a redshift distribution, it's going to shift the amplitude of a cosmic shear measurement. And that is highly degenerate with certain parameters of a typical intrinsic alignment models because it's going to shift the cosmic shear measurement in a similar way. So the idea is like, if you can find ways to sort of capture the information in the photometric redshift uncertainty, like that is more physical, you might get some like, and to model the intrinsic alignments in a way that accounts for these accounts for the relationship with the photometric redshift estimation, like, or with the galaxy bias, you might like gain something there, if that makes sense.
Yes.
Yeah.
I was just trying to understand what parameters could overlap and give this degeneracy.
Yeah. So actually, there's an interesting work by a PhD student at ETH Zurich. It should be coming out like next week, hopefully, where he's seeing that like, if I can't remember which way around it is, but basically the degeneracy between photo Z and intrinsic alignment modeling could potentially in some way go some way towards explaining the low sigma 8 values that you see from large scale structure measurements compared to CMB. So it can be quite important, even though it's not very glamorous. But yeah.
Okay, well, thank you.
Yeah, no worries.
I'll just ask if someone has a last question. Okay, we are already over. Well.
Okay, shall I stop
11,
sharing?
Yeah, it's 11 p.m. here. So, well, if there are no more questions, we will now wrap this up. This presentation will be available on our website and on the YouTube channel. Thank everyone for attending, and a special thanks to Dr. Leonard. Thank you for taking the time and giving us this amazing lecture. Well, everyone, have a great day. Stay safe, and I hope to see you all again on our next webinar. Thank you very much.
Bye.
See you, people. Bye-bye.